Have you ever stopped to think about what's really going on inside a battery? You know, the ones that power pretty much everything in our lives. Well, it's not magic. It's this amazing field of science called electrochemistry. So let's dive in and figure out how a few simple chemicals can create the electricity that makes our world go around.
Right. We see these every single day. They're in our phones, our laptops, the remote control, you name it. And on the outside, they look pretty simple. But the process happening inside, oh, it's incredibly clever.
And that is the million-dollar question, isn't it? How in the world do you get from a couple of chemicals just sitting there to a flow of actual electricity? The secret is all about harnessing a very specific kind of chemical reaction.
And here it is, the official sciencey name for a battery, a galvanic cell. Now, the most important word on this slide is spontaneous. That means the chemical reaction inside just happens. It wants to happen, all on its own, no help needed. Think of it like a ball perched at the top of a hill. It's naturally going to roll down. A galvanic cell is just a smart way to capture all the energy from that natural roll.
Okay, so let's zoom out for a second. Galvanic cells, our batteries, are really just one side of the story. In the whole world of electrochemistry, there are basically two main kinds of cells. Ones that make electricity and ones that have to take electricity to get their job done. And here is the fundamental difference, side by side. A galvanic cell, our battery, takes chemical energy and spontaneously turns it into electrical energy. An electrolytic cell, it does the complete opposite. It uses electricity to force a chemical reaction that would never happen on its own. It's like the difference between a waterfall spinning a turbine to generate power versus using a pump to force all that water back up the hill.
So let's stick with the maker for a minute, the hero of our story, the battery. As you can see, it's all about that spontaneous, ball-rolling downhill reaction. It's turning chemical potential into real, usable electrical power. And we measure this with something called a positive cell potential, which is really just a fancy way of saying, yep, this reaction is good to go and it's going to produce some voltage.
And then we have the taker. An electrolytic cell is what you'd use for things like electroplating, putting a chrome finish on something, or splitting water into hydrogen and oxygen. These reactions are non-spontaneous. You have to physically pump electricity into the system to make it work. You are literally forcing that chemical ball to roll uphill.
All right, so whether we're talking about a maker cell or a taker cell, they all share the same basic engine room. And that engine is built with two absolutely critical parts, the anode and the cathode. Getting these two straight is key to understanding everything else.
Now, this is probably the most important thing to burn into your brain. These definitions never, ever change. It doesn't matter what kind of cell you have. The anode is always where oxidation happens, and the cathode is always where reduction happens. A classic way to remember this is the mnemonic, Leo the lion says Jur. LEO, loss of electrons is oxidation. GER, gain of electrons is reduction. That is the golden rule.
Ah, and here we go. This is, without a doubt, the number one thing that trips people up when they're learning this stuff. If the anode's job is always the same, why is it negative in a battery but positive in an electrolytic cell? It seems totally contradictory, but I promise it makes perfect sense when you think about which way the electrons are flowing.
And this table just lays it all out perfectly. Look, in a galvanic cell, the battery, electrons are spontaneously created at the anode. It's the source of electrons, so of course it's negative. But in an electrolytic cell, you're using an outside power source to forcefully rip electrons away from the anode, which makes it become positive. See? The chemical job is the same, but its charge totally depends on whether it's pushing electrons out or having them pulled away.
Okay, so we know how the cell is built. But how much power does it actually have? How do we measure the oomph? You know, the force that's actually pushing those electrons through the wire from the anode to the cathode.
We call that force cell potential. And honestly, the best way to think about it is like water pressure. Imagine a really tall tank of water. The pressure at the bottom is massive, right? It's just itching to flow out. Well, cell potential is the electrical version of that. It's the pressure built up by the chemical reaction, ready to push electrons through the circuit.
So this brings up a really interesting little problem. This electrical pressure, this voltage, it only exists because of the difference between the anode and the cathode. So how on earth could you measure the potential of just one of them? It's kind of like trying to measure how tall a mountain is by only looking at its peak. You need a starting point, right? Like sea level.
And the simple answer is, you can't. It is physically impossible. You can't measure one without comparing it to something else. So what did chemists do? They all got together and agreed to create an official sea level for electrochemistry, a universal baseline that everyone on the planet can measure against.
And they called this baseline the Standard Hydrogen Electrode, or SHE for short. And they decided, kind of arbitrarily, but it was super useful, to define its potential as exactly 0.00 volts. So now we can measure any other half reaction against this universal 0 point and get a number that means something.
And that measurement gives us this value, the standard electrode potential. Basically, this number tells you how much a substance wants to gain electrons. A big positive value means that chemical has a really strong pull for electrons. It desperately wants to be the cathode and have those electrons for itself. Now, up until now, we've been talking about standard conditions, which is great for a textbook, but it's basically a perfect, pristine lab environment. The real world, as you know, is a lot messier. So let's see what happens when things aren't quite so perfect.
Exactly. What happens to your battery's voltage when it starts to get used up and the chemical concentrations inside start changing? Does that electrical pressure just stay the same? No way. And we need a tool to figure out exactly how it changes.
And here is that tool, the Nernst equation. I know, it might look a little scary at first, but its job is actually pretty simple. It's a formula that connects the voltage of the battery to the real-time concentration of all the chemicals inside. It lets us step out of the lab and into the real world.
Let's just break it down real quick. You start with your E0, the standard potential. That's your baseline value from the lab. Then you adjust that number based on N, which is just how many electrons are moving in the reaction, and Q, which is the ratio of your products to your reactants. That's it. It lets you predict the voltage under pretty much any condition. And this brings us right back full circle to our most important analogy. Seriously, if you remember just one thing from all this, make it this. A battery's voltage, its cell potential, is just like water pressure. And the Nernst equation is just a way to calculate how that pressure changes as the water level, the chemical concentrations, goes up or down.
So here's the big takeaway. A battery isn't just some static box with a fixed amount of power. It's a living, breathing, dynamic chemical system. Its power changes with things like temperature and concentration, which is why your phone battery dies so much faster when it's cold outside. By understanding this, we can predict, control, and even manipulate that power. And that leaves us with a really exciting question for the future, right? This science isn't just about the AA batteries in your remote. This is the bedrock for fuel cells, for massive grid-scale energy storage, for the next generation of power systems. So if we can truly master this idea of fine-tuning electrical pressure by tweaking chemical concentrations, what incredible energy technologies are we going to unlock next?